Okay, today's lesson 6.3 is on the Heaviside Function. This thing is also known as the step function. And as you might expect, it is piecewise defined. There's several notations out there. Your book likes to use A for this, but most of the conventions use C. So it's UC of t, and that's also the same as u of t minus c. And both these notations basically mean the same thing. What it basically means is this: it's a piecewise defined function that has a value of 0 as long as t is less than c. But once we reach c, then the Heaviside function changes to a magnitude of 1 for t greater than or equal to c. So it basically looks like this. Here's the u function, here's the value c, and its function value basically looks like this. It's 0 until we reach c, and then it jumps to a magnitude of 1, and it keeps that value from then on. You might wonder what a function like this could be good for. Well, here's one of its applications. Y double prime plus a y prime plus by is equal to r of t. This is the second order non-homogeneous linear differential equation that we've been looking at for the last couple of days. We've been using Laplace transforms to solve these. Well, suppose RT is actually piecewise defined. That is, suppose it's a mildly discontinuous function that actually leaps around to different values. That's actually quite common with the engineering applications of these. RT might be a function that is silent for a while, that is, it's 0, and then all of a sudden it leaps to a certain magnitude. Well, this function is perfect for stuff like that. So what we want to look at is, suppose we've got RT, and just suppose that RT actually looks like this. It's kind of like a sine function, right? Well, if I wanted this function to delay its beginning so that it didn't begin at t equals 0, but it began somewhere later, one of the ways to do that would be take UC of RT. And let's look at what that does. What it's going to do now is delay, like R, will start to perform whatever its function is until it reaches the value C. None of this will actually be there. This will all be 0 because UC has a magnitude of 0 until it reaches C, and then it turns into 1. So from this point on, it will just then continue with whatever RT was. So if I want to delay a function acting and have it be 0 magnitude up to a certain point, then the Heaviside function is a great way to do that. Now I might want another transformation. I might actually want it to delay and be 0 for a while, but then I might want it to actually begin at its original function value. And this guy's called a shift, so I'm going to time shift it as well as make sure it's 0 up to that point. So to do that, this is what we want the output to look like. We want it to be 0 all the way up to C, but then we want it to begin executing as if RT started at this point. Now to make this happen, I've got to both use UC, and then in addition, I have to transform R so that it begins at C as its initial point. And in order to do that, that's R of t minus C. And to see how that does it, once we're at C, it'll be C minus C or 0, and R will perform exactly as it did this point. It'll just move that over to C, and every point thereafter will behave this way too, all right? So here's 3 views. RT could be normally defined in some sort of continuous function like we've been working with up to now, or it could be a function that delays beginning its execution while it's still maintaining its function values as if it started at 0, or it's actually going to delay the beginning of the function acting, and it'll be 0 up to that point. So that's one of the applications for this guy, okay? Now, of course, in order to solve differential equations by the Laplace Transform method, if we're going to replace the right side of these differential equations with things that look like this or this, we're going to need to look at what the Laplace transforms of those are. So let's start that process. So I'm going to get rid of all of this, and we're just going to look at what is the Laplace transform of the Heaviside function. So what would L of U of C look like? Well, we know that the Laplace transform is the integral from 0 to infinity of e to the negative st times the function we're after, which is uc dt. Well, this is pretty easy. The integral is from 0 to infinity, and from 0 to c, this guy's going to return a value of 0. That's the way it's defined. So the bottom portion of the integral says, no matter what the integral of this is, if I plug in from 0 to c, this guy's going to return 0. So what I do instead is I start the integral at c, and it goes from c to infinity, and now uc has the magnitude of 1, so it's just e to the negative st dt. So the Laplace transform simply falls apart, and all we do is change the lower limit to compensate for what the step function, the Heaviside function, does to it. So now we just evaluate this integral, and of course that's going to be negative 1 over s e to the negative st, evaluated between c and infinity. When I plug the upper limit into this, infinity, because this is going to be a huge number in the denominator, it'll go to 0. And then minus, when I plug the lower limit in it, it's going to be negative of that. So it's 1 over s e to the negative sc. So there it is. The Laplace transform of the Heaviside function is 1 over s e to the negative sc, where c represents how we're defining the starting point of the Heaviside function. Okay? The Heaviside function can be used for a lot of other things too. Suppose I had a function f, which itself was piecewise defined. So it has some value f1 from 0 all the way up to when t basically is less than c, and f2, so it undergoes some transition when t is greater than or equal to c. Well, there's nothing wrong with this guy being piecewise defined, but of course that would create some difficulty if this guy were the r function at the end of one of these differential equations. I would want it to be indicated so it would be easier to take the Laplace transform of, so that I didn't have to deal with the differential equation under these different ranges. Well, there's a way to do it with the Heaviside function. I can rewrite f this way, because if we think about what the graph of this would look like, here's point C, and I'm just going to make up two, sort of things for f. This is f1, it rises, and then here is f2, it rises also. So here's f2. So the function basically changes from one to the other at the value c. Well, I can use the Heaviside function to do this too. What I want to do is say first f is equal to f1, because from 0 all the way up to c, that's the only portion of the output that I want to see. And here's where the Heaviside function comes in. Now I say uc times the quantity f2 minus f1. Now you might wonder what that quantity does. Well, remember, uc only exists once we're at c or above. So when we're below c, this part of the function is just 0. But once we reach c, this turns into 1. And look what happens to this function when this turns into 1 instead of 0. Now it's going to be f1 plus f2 minus f1. That's going to mean this guy only generates f2 from c onward. And that's exactly what we wanted. This guy then is just a single function. It isn't piecewise defined anymore, and yet it is. It still has the same output. So that's one of the big values of the Heaviside function, is it allows us to take piecewise r's and turn them into functions that are no longer piecewise defined. Okay? Now, of course, that means I'm going to need not only the Laplace transform of the Heaviside function, which I've got, but I also need composites of the Heaviside function times f when it's shifted and non-shifted. So let's take a look at both of those, okay? I'm not going to do the derivations of these. I'm just going to write them down for you. And again, these you will apply. So the first one is, suppose we wanted the Laplace transform of the Heaviside function times just RT. So it was that version of it where we want the Heaviside function to delay the beginning of the function generating values, but when it begins to generate values, it'll generate values at c and not 0. Well, here's what that is equal to. This is equal to e to the negative sc times the Laplace transform of whatever r is shifted. It'll be r of t plus c. So this is the Laplace transform of this version of the Heaviside function impacting the function, so it delays its starting values, but it doesn't delay at 0 point, okay? And then if we wanted to delay the 0 point as well, we would want the Laplace transform of uc times r of t, in this case it's going to be t minus c. Because what we want now is for the function to generate the same values it used to generate at 0, but we want it to generate those starting at c. So this is the version where it is 0 all the way up to the point where the function begins, and the function starts as if the function were at 0, and it does so at c. Well, what does this guy equal? This one's even easier. This is e to the negative sc times whatever r is of s. And this, again, is just the Laplace transform of whatever the function r was, okay? Okay, so armed with these, together with this concept of the Heaviside function, there's a number of different problems that we can apply this to, and the next videos will show you what those are.